I'm Christiaan. I work at QB Logic, where we do circuit design, and if we have the chance, we do that in Haskell. So I'm going to talk about the compiler that we use to turn Haskell into circuits. So we developed this compiler called Clash, and then if you look on the website, the first thing it says that Clash is a functional hardware description language that borrows both its syntax and semantics from the functional programming language Haskell. So it's a language in its own, but really it's just regular Haskell that you can compile to circuits. So when I talk, what I mean exactly when I talk about circuits, I don't mean like these kind of breadboards with all kind of wires connected. I really mean like chips like these, building these kind of chips using Haskell. So there's actually, as long as Haskell has existed, there's also been Haskell in circuits. And even just, so Haskell doesn't exist for that long. So, you know, we have, if you look all the way on the left, you see Hydra, which was a way to describe circuits in Haskell. That was 1995, but that was, let's say, the beginning of Haskell to begin with. And so before Haskell, there were other, functional languages exist for much longer. And so it actually goes way more into the past, where there was this marriage between functional language and circuit design. As you can see, so if you're familiar with Haskell, then most people will know like Haskell 98, but like before that, we already had how to do circuit design using Haskell. And then in 2001, we had BlueSpec Classic, which is also a Haskell-like language used for circuit design. One of the creators actually here in the audience. Hi, Leonard. And then there was this, for some reason, a large gap in terms of, published work. And then suddenly in 2009, there were like 3 approaches again. So we had York Lava from the University of York, Kansas Lava, which is from the University of Kansas, Andy Gill's group, and York Lava was Colin Runciman's group. And then there was us as well, Clash, and we all presented our work at the Haskell Symposium in 2009. And there's been some other work trying to use functional languages, but in a different way, or Haskell basically, to create circuits from them. So, I'm here at the programming conference, so I'm going to tell you a bit about the process of how chips are designed, and not their fabrication. So, you start, as with a program, you start with a specification, like what are the requirements, then you make a high-level design, and maybe a more detailed design, and then you start coding. It's not always true. Some people, as with programming, they dive straight into coding. That's fine. And then you do the functional verification and testing. This is usually a bit more important with chips, especially if you actually make hard silicon, because there's no do-over once you've created a chip. It's there, and it's really expensive to produce them. And so on the left-hand side, it's all coding, and on the right-hand side, it's usually just running programs that do all kinds of manipulation on your program code to turn it into polygons, basically, for the machine to draw all the transistors onto the silicon and connect all the metal layers. So that's the logic synthesis and the place and route step. That's where all the hard problems are for circuit creation. And then we have verification, fabrication. You actually create the chip. And then once you've created the chip, we call post-silicon validation. That really means like, well, you've built it, but maybe something went wrong in fabrication, and you want to check that as well. And so when you're building a chip, yeah, you do the coding part, and then, well, you do verification, and then you want to know, is it fast enough? Like, how fast can my chip run? And that's the logic synthesis and placement route. And compared to programming, this, let's say, this compilation cycle can be quite long. So for some of the designs that I worked on, it was 8 hours, but it's not unusual actually to have 24 hours or more. So you start multiple runs with multiple ideas, because it won't be until the next day until you get an answer whether your chip was actually fast enough. So for this RTL coding, the description of the hardware, the industry uses mostly two languages, Verilog and VHDL. And then for functional verification, making sure that what you described in VHDL or Verilog actually work, well, you can either use these two languages. They have some abstraction mechanisms that enable you to do testing, do some higher level programming in them. But what you see in the industry is that they use all kinds of languages, Python, C, C++, Tickle, Perl, you name it, is used to then verify that the chips actually work. So what we're trying to do with Clash, or with Haskell really, is take the entire left-hand side and do both your, even at the highest level, try to use one language and also do the coding, like sort of massage your high-level specification that you've written in a functional language, and add some features, some details, so that it is going to work well as a circuit. And so you never have the problem which you have with the previous approach, that you write something in one language and then you sort of hope that what you've written in the other language is going to be the same, with no way to check it mechanically. So I've talked a lot about circuit design and Haskell, but I haven't really talked about how you can interpret a functional program as a circuit. So that's where we start now, right? So on the left-hand side, we have some Haskell code, and on the right-hand side, we have its diagrammatic representation. So I'm mostly gonna talk about small circuits. I'm not going to go down all the way to the transistor level. I'm just going to talk about, let's say, these basic blocks, the basic logic gates, and how you can interpret your Haskell program as a combination of logic gates. So on the left-hand side, we have our half adder. It's a very basic circuit that can add 2 bits. So we have the 2 input bits, A and B, and we produce the sum and the carry, where the sum is defined by the exclusive OR of the 2 input bits, and the carry is defined by the conjunction or logical AND, or binary AND of A and B. And what you can see is that Haskell's, or in functional languages, really is that in a language like Haskell, there's not really like in many imperative languages a way to step through the program and follow the semicolons all the way down, right? So the where clause just defines the sub-expressions, and as you can see, because there's no relation between the sub-expression that defines the sum and the sub-expression that defines the carry, they can be evaluated in parallel. So that's what you see on the right-hand side. So the exclusive OR gate and the AND gate, they are just there simultaneously computing. So that's a real benefit of using a functional language where you only have to follow the data dependencies if you want to translate that to a circuit. There's a very natural mapping. And actually, in pure functional languages, you have extremely fine-grained parallelism, and that maps actually really well to digital circuits. Whereas, let's say if you want to do multi-core programming, like maybe you have like 12 cores or 16 cores these days in your desktop, and there you have to, group everything together, and that's a difficult problem. Like, which instructions should you group on what core? And you have to really think hard about it. But on circuits, you have extremely fine-grained parallelism, and so a pure functional language like Haskell, it maps really, really well onto these kind of circuit descriptions. And so then when we go down, what we see here, so this is a more general case. So we have a function g with 3 inputs and 1 output e. And in the where clause, we have 2 sub-expressions, and we have 2 functions p and q. And what's really important in the way that we within Clash view Haskell is that whenever we apply a function, that turns into an instantiation of the circuit that corresponds to that function. So in a way, you're basically inlining, right? There's not going to be one version of P that's going to live on your circuit, and we're going to wire every call to it. Every time you call a function, it's going to be instantiated right there in your circuit. And so this is how you're going to make trade-offs on how large your circuit is going to be by how many times you're going to basically apply a function, or you're going to apply it once and then just route multiple inputs to that function, like do a case expression basically for the inputs. So I want to move now a bit more to how to deal with choice concepts like if then else or case expressions. So here we have a simple counter circuit, 2 versions that basically express the same kind of logic, just written differently. And this is more to show that there's freedom on how you want to write your circuit, in Haskell, however you feel like. Clash is really more of a semantic subset of Haskell than a syntactic one. It's really full-on Haskell. So we have a counter that can wrap around at any point. So that's the first argument. Then there's the direction. It can either count up or down. And then let's say the value that you want to add to. So I call it a counter, but later on we'll have a feedback loop, basically. And so what you see is, so you have a case statement. So are you counting up or down? And then if it's smaller than the wraparound point, then you add or subtract. And otherwise, you go around to the wrapping. So if you count up, you wrap around to 0. If you count down, you would wrap around. You would go to the wraparound point. And so what's really important here is that in this case expression, so the alternatives are going to be translated to circuit, and they are going to be there simultaneously, right? So the circuit is going to evaluate basically both sides of the case expression concurrently, simultaneously. So that right, and then based on, let's say, the value of direction, we're going to choose one of those alternatives. So that's the trapezoid block. That's what we call a multiplexer. It's going to choose between those alternatives. So we translate case expressions or other kind of choice constructs to such a multiplexer. So the multiplexer is going to have, multiple inputs, and then the selection input, which in the diagram is like either in the top or the bottom, selects which flow we're going to take. And so this only works the way you can only do this translation if you have basically side effect free programming or extremely restricted side effects, because otherwise it doesn't make sense. Like if one of those alternatives would be some arbitrary global state manipulation, then you couldn't really do them concurrently, because like which world do you live in? Right? So, but in a pure functional language, you can translate case expressions to circuits that are highly concurrent. So you might think like, well, we're in a pure functional world. Like how are we going to basically build interesting circuits that can remember stuff about the world? So how do we introduce, let's say, state? And so the way we've done that in Clash is by working with programs that work on infinite streams. So on the top, you have a diagram of a simple counter that just increments by 1 indefinitely, starting from its reset value. And in the bottom, you can see what we call in circuit land a wave diagram. So there's the clock that is going to dictate the progress of the circuit. Then there's the D input. There's the D signal. That's the input to the register, which is like a very basic memory block. And then, as you can see, at every rising edge of the clock, as long as the reset is not asserted, the Q output is going to take over the value that's on the input. So Q is going to turn into 1 at the rising edge of the clock. But that means that, so then the register is going to output 1, that's going to go through the adder, and so the input to the register will be 2. And so then on the next rising edge of the clock, the circuit, the register will take over the value on its input, so it will start outputting 2. And so then the D input becomes 3. So the way we've done this, so the way we represent this world in Clash, in basically the base library for circuit design in Haskell, for our base library for circuit design in Haskell, is that we model these kind of streams in this data type that we call signal. So we have a signal A, this can be any type, and it's just an infinite stream of these values, and they correspond exactly to the values that you see on the bottom of the slide. And so then the most basic version of this register basically is we have some reset value, some starting value I, and an incoming stream S, and all it does is prepend the reset value to the incoming stream. And so this register is really that simple to model. And then we can create this adder circuit. The addition is also going to work on streams because we can just lift addition to the signal level, where we just do pairwise. So we take the first 2 values. So we have 2 signals. We take the head of that, we add them together, and then we continue doing the rest. And so now in the middle, you have the diagrammatic representation of the circuit. And then on the right-hand side, we finally have our Haskell representation. And so again, so we have the counter, and its output value is S, which is a stream. And then the stream is defined in terms of itself, because if you look at the circuit, there's a definite feedback loop. And so in Haskell, this is not a problem due to its lazy evaluation mechanism. So we can see that in Haskell, we have a feedback loop as using the tying the knot type of recursion, and that maps really well to a circuit. So I've said that Clash is Haskell, but this is the base library. So those of you who are familiar with Haskell probably know that there's basically, these days, there's one compiler called GHC, Glasgow Haskell compiler, and it has a lot of language extensions. And I think we don't use all of them, but we use many of them. And I'll tell you a bit in why. So it is regular Haskell, but a lot of language extensions turn on as well. And that's because in hardware, or the way that we view hardware within Clash, we want to translate everything to very parallel circuits, interpret a Haskell program in a way as a structural description of the circuit. And so we need to know how big everything is, right? Yeah. So if we have, we could have, like Haskell's integer is unspecified, like it's an arbitrary sized integer, and can grow as large as it needs to be. So that's really difficult to translate to hardware. And the same with, Haskell's regular linked lists. If you have a linked list as the input or the output of your, top level of the entry point, basically, of your circuit, then we have no idea how many wires we're going to need for that input. So in Clash, we really need to know how large everything is. So we sort of have dependent Haskell. And one of the data types that are somewhat ubiquitous in Clash, where, let's say, linked, Haskell's list type is ubiquitous in at least the standard library. In the Clash standard library, the vector type is the ubiquitous type, which is, again, a linked list, but it has the number of elements annotated in its type. So we have the nil constructor that has 0 elements, and so and then the cons constructor can add an element to a vector of length n, and then you get a vector of length n plus 1. And in this way, we know exactly how many elements there will be, and we know exactly how many wires we'll need to put down for our inputs or for our outputs. And then you can do crazy stuff as well, because it's dependent Haskell. So you can actually, so normally you have a fold that goes to a single element, but now, don't look too much at the code if you're not really Haskell, but basically, I wanted to have some fun, and I never show this function to any circuit designers, because they would go, the fold is already crazy for them, but then the dependent fold, where the output type depends on the length of the vector, that's just too much. So that's the reason why we can't just use regular Haskell. We need all of the extensions. I'm actually very grateful that these extensions exist, otherwise it would have been very hard for us to actually build a Haskell to hardware compiler. But that's not all. So you have lengths, right? But GHC's type inference engine is really good, but it was never built for symbolic manipulations of the natural numbers. So there's a lot of so if you're working in dependent types, people really like to work with proofs. But if you're designing a circuit, even if you're just doing programming, like, proofs are fun, but they're not fun for the things that you were taught in primary school math. Right? So you don't want to write down the proof for that every time, or type in search somewhere for the proof search. So one of the things that we get in Haskell is that, it doesn't know about the basic rules for algebra of natural numbers. So it says, like, oh yeah, you provided me with a vector that is length n plus m, but I needed it to be m plus n, and I have no idea that those two are the same. So that's fine. But then in circuit, we really deal a lot with powers of 2. So it also doesn't know that, if you take two that are one size smaller, and if you add them together, you get then the same size again. So also dealing with exponentiation, it doesn't know about that either. So that's why, again, so on top of all of the language extensions, we then also needed to extend GHC's constraint solver to teach it about primary school algebra, which makes it, let's say, a way more convenient for you as a user. So proving things is fun, but having to tell the compiler every time about the commutativity of addition is not fun. So that's where these plugins help out. How am I on time? Good, okay. So, yeah, I've shown like how to interpret Haskell as a circuit, the type of advanced stuff that we, that we needed to do to get to be able to translate Haskell to circuits in terms of the length and those kind of things. Why we needed, let's say, dependent Haskell. So now I'm going to tell you about how we build a compiler. Actually, when we started in 2009, it was me and Matthijs Kooijman, and it's actually his idea to use the GHC API. After that project, I continued with it. So the Clash compiler is really built on top of GHC, the Glasgow Haskell compiler, and the Glasgow Haskell compiler does a lot for us. So it takes in Haskell source files or precompiled Haskell, HI files. It does, so we take that from the regular Haskell compiler, so the parsing, the type checking, and then an important part, the so-called desugarer. So Haskell, it has a lot of syntactic constructs, like you saw in the beginning, like the way we could do the counter, right? There were many ways to represent the same circuit. Like many different, you have guards, case expressions, if, pattern guards, you name it. They have a lot of syntactic constructions, all to represent choice. In core, there's only one construct to represent choice. All you have are case statements. So even an if then else is translated to case of true, and don't care, it's translated to, and else is translated into the don't care case. So core is really mini Haskell. It's the BNF grammar basically only has like 12 constructs. Now the GHC API is not really an API, as in it's not stable, it's not really nice to work against as a programmer. Yeah, people have referred to it as the GHC assortion of modules. And it's really fluid, it changes all the time. And that's because, well, they basically expose the internals of GHC as a library, but they are also constantly changing GHC, and they just, the functions that I care about, at least, they change all the time. So what we've done at a certain point in the development of the Clash compiler is we said, yeah, all right, this is enough. I'm sick and tired of having to do CPP pragmas to know which version of the compiler I'm programming against. I'm going to translate just GHC's core to my own core and provide a stable API. So first we get all the core from GHC, then we translate it to our own core data type, where core is really this mini Haskell, a language with only 12 constructs. Then comes basically the meat of the Clash compiler, which is the normalized stage, which I'll go into after this. And it translates this mini Haskell to a version of this mini Haskell that's trivially translatable to a circuit. So yeah, the mini Haskell to circuit normal form, that's the non-trivial part. And then once we have it in a normal form, a form that's where really the normal form means trivially translatable to a circuit. And then we can either, so we get like a netlist, which is really just the graph of the components, and we can render that to VHDL, Verilog, or System Verilog, these industry standard languages. And we do that because, well, we want to work with the tools that the industry already creates, and those tools only understand these two languages, basically. So that's why we emit VHDL and Verilog. instead of going even lower level form, it doesn't make sense. If you produce these circuits in these languages again, you can just use the industry standard tools from there on. So I talked about, let's say, trivial trivial synthesis, or like, and so how does that? So how do we do synthesis? Basically, how do we turn a program into a graph? And here we see a very simple first-order functional language. Like, you only have functions definitions. So if you look at the top with some arbitrary number of inputs, and that there's an expression on the right-hand side of that function definition, and then you have perhaps more, and then there's also the main function, which is basically your entry point. Like, so that's the grammar of function declarations for this very simple first-order language. And then at the bottom, we have the grammar for expressions. So you either have a reference to one of your arguments, you apply a primitive operation, let's say addition, or you call one of the functions in your program, right? So that's the grammar for programs. And so the trivial translation now is really just a syntactic translation from programs that are emitted by this grammar to circuits. So whenever we see, and so now we go to the bottom diagram, right? So whenever we have a function application on some arbitrary inputs x, like we turn that into a basically a new block representing this function f. We connect all of the arguments, and then we go inside of that block and translate the expression. Now, argument reference is very simple. We just connect to one of the reference arguments. And yeah, so and then primitive definition, what you see on the bottom right is just that we instantiate a primitive. We connect, we translate the arguments again recursively, and we connect those to the inputs of the primitive. So there's a very straightforward, syntactically directed translation from a, let's say, a first-order functional programming language to circuits. So that's what we like. So this net list is really this very syntactically directed translation to a graph that represents the circuit. But again, so systemfc, which is the Haskell mini language used by Haskell, used by GHC. So on the left-hand side of what we see on the screen now is the grammar for the types. You can really not care for that. So if you looked at your top right, that's the entire grammar for expressions. I said 12, I'm not going to count them, so maybe there's 14, I don't know. But so you can express any Haskell program using these constructs. And then what I said about once we have this normal form, so if we have a grammar for, if we take a limited shape of the original grammar, then we get this very straightforward translation to graphs again. So, if we have at the top level expressions, if we have a lambdas for all of our arguments, then we have a let expression, and then in a variable reference, then that variable reference in the body of the let is going to be the output of the circuit. All the lambdas are going to be the inputs to the circuit. And then everything in the let expression is going to be, let's say, our sub-circuits within our larger circuit. And again, so variable references, they connect to, they can either connect to one of the arguments or they connect to one of the outputs created by our sub-circuits. And function, function definitions are again, so we create a box for the function application, right? So we create a box for the function that we are instantiating, and then we go inside of that and translate it. And yeah, top right, primitive or applications of primitives. And we've already seen in the counter example, the example of the counter, that that we can translate case expressions to this multiplexer, right? This basic circuit that can select between alternatives. So once we have like our mini Haskell in this very reduced shape, or like, then it's trivial to translate to circuits. So to give you an example, so on the top left we have Haskell again. So depending on the first value, so the first argument x, we either add 2 to the multiplication of its other arguments. So a and b, we multiply them to give us y, and we either add 2 to y or we multiply it again. And so that's regular Haskell. And then in the bottom left, you can see this mini Haskell, this GHC core with this reduced version of Haskell. And there we can see that, well, first of all, every binder, every argument or let binder is annotated with its type. So we have the lambdas to represent the arguments. What we can also see is that, they messed up with the rendering there, but there's, so in Haskell, we could see that we are pattern matching right away on the tuple of A and B, but in mini Haskell we don't have that syntactic equivalent again. We don't have that syntax, so we get one argument called ds, and so we pattern match on that to get the A and B. So that's the first case statement that corresponds to the Haskell pattern match on the A comma B that's translated to a case statement in systemfc. And then where clauses are always translated to let expressions. And like I said, the if then else is translated to another case expression. So bottom left is regular FC. And then if we have normalized FC, the one that gave us the trivial translation to a graph, that's what you see on the right-hand side. And I guess the only thing that I have to introduce there is this pi, with the subscript. That's basically a projection. So if any product type, if you want to extract one of the values out of that product type, whether it's a vector or a tuple, I want a certain argument or a certain field out of that product type. That's what the pi is for. And so on the right-hand side, we have this very normalized FC. And again, we have a very syntactic, trivial translation from Haskell in normal form to the circuit on the right. So yeah, again, if we Haskell on the left and then a prettier looking circuit or a less mechanically looking circuit on the right-hand side, but it's basically, so the circuit that you see here on the right is really the same as the other circuit you see here on the right. It's just compressed a bit. How am I in time? Good? Okay. So so on the left-hand side, we have our grammar, right, that can represent arbitrary Haskell programs. And on the right-hand side, we have this reduced form of the grammar. That's where we said there's a very trivial translation. And so when I said, well, where the meat of the Clash compiler is that it's manipulating your program that you had that was emitted by the grammar on the left-hand side and manipulating it in such a way that it will be accepted by the grammar on the right-hand side. And that's really by something that has been done for building compilers for functional languages for a very long time. It's just by a process of repeated rewriting. So we have rewrite rules that take a expression in a certain form, and we rewrite that to a expression in a different form. One of the simple ones there is that if we have an application of a Lambda expression, so something that takes an argument, then what we do is that, so we have the Lambda expression with its body E, right? And we substitute every encounter of A by the argument tau, basically. So this is how you make the expression smaller. So you used to have an application of the Lambda and an argument, and now we just substitute every tau for any reference to alpha. And this is fine because this is actually for type substitution, not for term substitution, because if we would do the same for terms, we would basically make our circuit a whole lot larger, because here we see on the right-hand side how we do it for term level lambdas, so lambdas that represent, let's say, regular arguments instead of type arguments. So there we have a circuit, let's say, represented by U. If we would then substitute that into E, that would basically mean that we are going to duplicate the circuit in E as many times as X was referenced in E. So that would make the circuit a whole lot larger. So that's why we do what people in the program theory call, let's say, lazy path reduction. So we turn it into a let expression. It's not necessarily smaller, but it helps us get rid of the lambdas. And so there's a whole lot more. These are just a couple of examples. But basically, once you have enough of these rewrite rules, and you apply them exhaustively, you can guarantee with certain restrictions on the top level that any program that's emitted by the left-hand side can be translated to a program that's emitted by the grammar on the right-hand side. So that's really doing all of these rewrites is really the meat of the Clash compiler. But of course, there's remaining challenges. We're definitely not done with our work. So there's a lot of issues on the GitHub issue tracker, sudden non-termination, sudden explosion, quadratic, well, that's kind, might sometimes be exponential, bad runtime complexity, Clash inliner, can't even, yeah. Bad, basically. So one of the remaining challenges that we still have is in this issue called partial evaluation. Something that people and compilers always want to work on. Well, some of them at least. So that's really, so Clash, through its rewrite system, accidentally does partial evaluation, which is where the problem lies, because it doesn't do the smartest traversal through the expression tree. It doesn't. It duplicates a lot of work. Yeah, but yeah, the issue is that it's also somewhat of an open research question how to actually do partial evaluation for a non-strict language that has recursive let bindings. And with a slightly different performance metric, which is the size of the circuit. So there's actually, let's say, paper-worthy research that still needs to happen on that side. And, well, that's why we've punted it for now. We know of ways to work around the limitations of the compiler, basically. But so yeah, there's still an open research question on how to do this properly. But we have been, so not just us, but other companies have been using Haskell for actual circuit design. So I'm going to first talk about a project that we as QB Logic did with a partner. There we worked on laser-based satellite communication between a ground station and a satellite. And this was a terabit, in terms of bandwidth, it's a terabit per second. But as you can imagine, like if you have a ground station and some satellite, there's the atmosphere in between, and that kind of distorts the laser. And we want to correct that for that on the ground station using mirrors and all kinds of contraptions. And we need to adjust those mirrors very quickly, and that's why we needed an FPGA for that. An FPGA is a field programmable gate array, so gate array really means that you can sort of emulate a circuit that you would normally hard bake into silicon. You can still do all kinds of manipulations. And the field programmable means that you can program it in the field. You can change it on the fly, basically. So we can sort of, we have like a reconfigurable chip, which is the FPGA, and then we baked it, or we changed it in such a way that it behaves like the circuit that we wanted it to be. And that controlled all of the mirrors to achieve the terabit bandwidth. And so that was all built. So we started with a high level, and then we manipulated in a way that we got nice performance metrics. Another company is a company based in Cambridge, UK, called Myrtle AI. They've been building accelerators for deep neural networks. So they realized that, well, CNNs or convolutional neural nets, like you should just use a GPU for that. So they started focusing on other kinds of neural nets. So they've looked at LSTMs and other kind of neural networks. And then they built a real-time text-to-speech synthesis engine with the human-level quality audio. It could do, on a single FPGA chip, it could do 256 simultaneous streams, which when they developed it was 8 times faster than state-of-the-art on the single chip for this particular neural network called WaveNet. And what was, well, for me, was really cool was that it was actually, so Intel released a new FPGA that was what they called AI optimized, which basically means it had native support for dot products. Yes, so Myrtle developed the first, let's say, publicly, public third-party application, and was prominently featured on Intel's website, and it was written in a functional language and then translated to Clash. And as you can see, it was fast as well. It was 8 times faster than state-of-the-art, which was on a GPU. So FPGAs are really becoming a lot more mainstream. You might not have heard of them, but they really are. So FPGAs had their space a lot in the embedded world, automotive, or in the military, kind of radar. They've been used for a very long time in high-frequency trading as well. But now you can just buy them as PCIe accelerator cards from Well, so Xilinx has been recently bought by AMD, or merged with AMD. So now you have two big vendors, AMD and Intel, that both produce PCIe cards. Okay, thanks. And you can even rent FPGAs in the cloud these days. So AWS has its F1 program. Azure has their NP instances where you can run FPGAs, and there's specialized vendors like Nimbix as well. And yeah, for example, Samsung, together with Xilinx, is supplying SSDs with FPGAs built in, so you can do certain types of encryption and other kinds of things at the bandwidth that these SSDs can handle. So really, yeah. So for certain applications, you need more speed than what regular CPUs can offer. And then now with Haskell, you can actually target these, very specialized chips really well. So there used to be this idea that any high-performance code needs to look imperative, because that mapped really well. So here's C between quote marks, but that could be, Haskell written with, unsafe, or with IO refs and ST refs, or anything that has to do with mutable state. That meant like you can run it fast on your CPU. And then, so there's GHC, but also other compilers in the past that basically did the Herculean effort. So Haskell is not a language that, if you look at the evaluation mechanism, looks nothing like how an actual CPU behaves, right? So, it's been really, great effort or great result, actually, that they've been able to, put a language like Haskell and run it on a regular CPU. But now, with the love of Clash, we can just put Haskell on the target it was always meant for, and there's this long time, as I said in the beginning, long time marriage between functional languages and hardware. You can really use the fine-grained parallelism and fine-grained concurrency that you always had in your programs, and you finally have now a target where it really maps well to, which is circuits, and you finally let the dream of fast Haskell, come together using Clash. So yeah, I invite you all to take a look in Clash and install it. This is the website. What I found really exciting recently is Gergo Erdi. He wrote a book on Clash. It was really cool for me to see that somebody else wrote a book about the program that we've been working on for such a long time. It's retro computing with Clash, so it teaches you how to use Clash to build architectures from mid-80s, CompuColor 2. You're building Pong, and there's a complementary GitHub repository with easy scripts, so you can put the code that you write and put it on the FPGA boards. And we're helping him now to port it to multiple FPGA boards as well. And with that, I want to thank everyone and hope you have some questions.
Thank you, Christiaan. So yeah, people in the room, do we have any questions?
Thank you. It's been a great talk. I'm wondering about the extensions. So you mentioned that Clash uses core and takes over from GHC from core. So I was wondering which version of GHC is the latest Clash on, and the second part will be, are there any extensions from GHC that are actually prohibited to be used?
So, like currently Clash runs on GHC 9. I skipped 9.2 for reasons, and I'm now trying to port it to 9.4. In terms of language extensions, no, all language extensions are fine. It took us some time to support GADTs. That's relative, well, there was recently a bug in one transformation, but let's say in the general sense, GADTs should be supported as well. Yeah, there's really no restrictions. There are some, so you can tell GHC to do certain optimizations, and some are, let's say, not beneficial for circuit design. Yeah, if you're really deep into GHC and Haskell, the worker wrapper transformation does nothing for Clash. That'd be my answer. Thanks.
Okay, we have another question.
So in real life, for Signal, it takes some time to switch from 0 to 1. So, and do you somehow model that in the Clash?
No. So we really only model synchronous hardware. So we really so we model what we call the stable values as the values that you have in the stream, and what we don't model is how long it takes for the signal to propagate. And so if you want to, so what really determines how, you have the people that don't do much circuit design. So you have this clock signal that indicates how fast your register can take over its input. But that input needs to be stable. So that's for the propagation. It takes time for the circuit to propagate through all of the gates in there. And it needs to be stable before you should copy it. So the longer the more functions there are between one register and the other, the lower your clock frequency must be. And so Clash takes a very syntax-directed approach. So if you want to increase your clock frequency, then you should really just manually place a register in between a long path, between a lot of operations, so that you can increase the clock frequency. So then you have fewer operations between every register. But it is, because we don't model it, you do depend on the vendor tools. So you generate VHDL, then you do it through the vendor tools. It will tell you like how fast can your circuit run, or actually, usually the way it is, you want to run the 50 megahertz, and then it tells you like, no, you can't. It's 2 nanoseconds too slow, and the longest path is here. Then you need to go back to your Haskell and fix that.
Any more questions? Okay.
Yeah, thank you for a wonderful talk. So you're replacing the whole stack of languages by Haskell. How did the users, programmers react to that, and how much did that inform sort of your final product? If you could talk a little bit about that.
So yeah, it started out as an academic project, so we just went ahead in what we thought was nice. It resonates with certain. So usually circuit design is done by people with the electrical engineering background, and for many of them actually, let's say the concept of programming, which they then think means C, doesn't resonate with them at all. They like what, it's so sequential, has nothing to do with the analog circuit that I've been designing at all. And so some of them really like that aspect. But I think, so what we usually show them is like, let's say, basic Haskell, and then they think that's really, really nice. And also, for example, so at the university previously, we also taught Clash to embedded systems students, and they actually grasped things like higher order functions really well, because we would show like how a fold corresponds to, you know, a linear succession of functions. And so they actually had, so they understood that quite well. But if you then look at the industry as a whole, it's very conservative for, let's say, good reasons as well, because it's expensive if you make a mistake. So yeah, it's an ongoing process of conversion.
What would you say are the main advantages from the programmer perspective or from the business perspective when using the Clash over the VHDL?
So from the business point of view is that because you stay in one language, there's a lot less bugs in between. Like in standard ways, sometimes you have a high-level specification in one language, and then you give it to a completely different team that tries to interpret that and turns it into a circuit, and there's mismatches in between. If you stay within one language, you avoid those kind of mistakes. Another aspect is just being able to work in the, so for me personally, what's been, so aside from being able to work in a regular programming language with all of its abstractions, is just having, so within Haskell, having the ability to have the interactive interpreter available and test quickly. So, but from the client's perspective, is that if you look, so, you know, but let's say you do an estimate of how long something should take, right? There's always, like, it might be, you might have it done faster, but usually it takes a lot longer than your estimate. We think with Clash, because we can make fewer mistakes, we can, if you look at the distribution of your, of the timeline, right, we can shorten the tail. It doesn't mean that the mean might still be at the same exact spot as VHDL, as in we can take exactly as long, but there's more of a guarantee that it will hit the mean instead of being in the long tail end where you go from 1 year to 2 years for your project. That's what all of these effects sort of compound.
We also have some questions from our online audience. I'm not sure if you can see it. Is it possible to model quantum circuits with Clash?
No. And so I think, well, it's been some time since I looked, but usually if you have quantum circuits, like they need to reach an equilibrium and things can flow both ways. And in Clash, so in Clash, really, we have a functional circuit and information flows only one way. And I believe with quantum circuits, you need to, information sort of flows both ways. So if you would have a relational language, which has been developed, that might be a better fit.
Is there any constraint about wires not crossing? If yes, is it solved by Verilog VHDL for you, or does it need to be dealt with in the Clash compiler?
So yeah, if you build a chip, then there's a limited amount of what we call metal layers. And I think, so normally if wires cross, you would just go into a higher layer and then go down again. And that's really not solved by us. So I talked about the synthesis and place and route, and they tried to figure out a crack path. And so that means that, so wires they can't always be drawn in a straight line from one point to the other. Well, and so on FPGAs, you have routing resources, and you might have used too many, so now it needs to route the signal, because this router is already full, it needs to route it around. And same with ASIC design, at a certain point you run out of metal layers, so then it also needs to take a detour. So yeah, it's not handled by us, and if it shows up, then you could fix it in Clash by doing either placement constraints or doing something on your logic that you have what we call fan out. So normally if you have one logic function, it can go to multiple different places. And what you then might do is actually somewhat counterintuitive, but you take your circuit and you duplicate it. So it lives here and lives there, and then from one circuit it can route to some places, and from some other place it can route to other places, and with that you can reduce congestion at the expense of having more gates. But ultimately you have the circuit that behaves according to the specifications that you want it to be.
Okay, any more questions in the room? Okay.
Aside from us liking functional programming languages, are there any advantages to using Clash instead of, say, something like System C that's more imperative style for the input hardware description language?
Any advantages? So programming and circuit design are really I still consider them a creative process. So if the style of System C resonates with you more internally, then pick System C. If the functional style, and I've talked to some functional programmers and they think, like, when I show them Clash, like, yeah, I've always thought of my programs as sort of data flow diagrams. So if that view of the world resonates with you, then you should pick Clash. You'll be more efficient with that than you would be with System C. I think some of the testing libraries in Haskell are really great. So a lot of the languages out there have constrained random generation, but there aren't that many. Well, I know I know Erlang has this as well, thanks to John Hughes. But really, John Hughes' work, like on Quick Check. But really, the shrinking aspect, that's been really awesome for us because, normally if you have a circuit, then it takes time. And so you might have random generation, and it says, at cycle 50, something went wrong. And then you're looking at so I showed the waveform diagram here, it's only 2 signals, but then you're looking at 100 signals and trying to figure out, where did it go wrong? And with things like Hedgehog or Quick Check, that we have the shrinking aspects, and it can reduce it back to 5 cycles. It's really awesome to have. And as far as I'm aware, they do have constrained random generation in many System C libraries, but they haven't done shrinking. But it's not really a limitation of the language itself. It's just that perhaps they're not familiar with shrinking yet.
Okay, I'm afraid we are running out of time. But please do remember that our speakers are here with us, so they can still answer your questions in person or in our meet as well. So let's give another round of warm applause to Christiaan for the great talk we had.